Good day and welcome to Chem Help ASAP. In this video, we'll demonstrate the Knoevenagel condensation and prepare a substituted coumarin. We will discuss the reaction, perform the experiment, isolate the crude product, and characterize the material. This specific reaction was requested by a viewer. If you have a reaction request, do not hesitate to say so in the comments. If the reaction is fairly easy and I have the reagents on hand, I will try to do a video. The Knoevenagel condensation is a type of aldol condensation, so the product is often an alpha beta unsaturated ketone or similar compound. The enolate in the reaction is stabilized by two strong electron withdrawing groups, often a ketone, ester, nitrile, or nitro groups. To perform the condensation, the central carbon must be a CH2 group. A methylene. These types of compounds, a methylene with two electron withdrawing groups, are called active methylene compounds. The electrophile in the Knoevenagel condensation is very often an aldehyde. Because of the strong acidity of the alpha carbon in the active methylene compound, weak bases are often used for the Knoevenagel. Amines are common. The Knoevenagel is a very old reaction and dates back to the very late 1800s. Here is the specific Knoevenagel condensation for this video. The active methylene compound is ethyl acetoacetate. You can see that there are two electron withdrawing groups, one ketone and one ester on the CH2 group. The electrophile is salicylaldehyde, a substituted benzaldehyde. I followed a literature procedure for this reaction. The procedure, cited at the bottom of the slide, used piperidine as the base. I couldn't readily put my hands on piperidine, which has this structure in the upper right, so I used morpholine instead. The base is catalytic, so substituting reagents was not an issue. The reaction has no solvent. You just mix all three reagents and warm them gently. The aldol condensation gives this product. There's the ester and the ketone. The ester and alcohol subsequently undergo an intramolecular esterification to form the new ring. Compounds with this core bicyclic structure are called coumarins. Coumarins are an extensively studied family of compounds. They have been found to have a range of biological activity: anti-tumor, antimicrobial, anti-inflammatory activity. One very widely used drug that is a member of the Coumarin family is the anticoagulant warfarin. The brand name of warfarin is Coumadin, which is a play on the core Coumarin structure. Okay, let's see this Knoevenagel condensation. All right, it's always good to be at the balance. Let's go ahead and get this reaction set up. So I have our first reagent. This is salicylaldehyde, and this is a liquid, and we're going to weigh this out on the balance. Now, weighing liquids out on the balance, there's always mistakes that can happen. You don't want to drip on the pan, so I've put this weighing paper on the pan, but this is just a 20 milliliter beaker. So let's go ahead and get started with our salicylaldehyde. And I am not going to be super careful at all. I know what I want. I want about 6.11 grams. And so I'm just going to transfer this by pipette until I get very close to 6.11. If I go a speck over, that's okay, as long as that speck is not too big. Okay, that's already 5.8. We're getting close. Let's get, so 5.11, I'm sorry, 6.11. Better slow it down. Oh, that is 6.110. Look at that. Okay, 6.11. Fantastic. You know, that might have been a little lucky, but that's okay. Okay, I wanted to move that. You saw me try to move that, but I don't want to move it because I have a second reagent. I'm just going to add the other reagent right in this same beaker. And be careful with this. This is ethyl acetoacid. As you can see, this is probably a collector's item. This is an old reagent, but that's okay. Lots of these reagents have a very good shelf life. And this will be just fine. So I want to, before I get too eager, let's re-tare. So I've got a nice 0 there. Now I want 6.51 of this. Oh, did you see that? That's going to be a little bit of error. I got to drop on the balance. It's not going to be a big error, but let's not deny the fact that was unintentional and not what I wanted to happen. It's okay. I know that I need to put something on the balance when I do this because a stray drop here or there happens. Now, this is enough that I could actually measure this out as a volume, but it's just so much quicker and easier to weigh this out on the balance that I can't let go of the simplicity of doing it this way. Okay, I don't know why I'm going so slowly. That's about 6.2, 6.3. See, 6.48, 49. One drop will do it. 6.517, we'll call that 6.52, which is a touch over, but that won't be a problem at all. And note, it's a little over. I also lost a drop here, so we'll still call that 6.52. And now we're done. We're done dispensing these two reagents. The third reagent I will add once it goes in the hood. Okay, we're now in the hood. Our same beaker, 20 milliliter beaker, has this liquid in it. I'm going to say it's about 12 milliliters of liquid. I have a very small stir bar in there. It is stirring. We'll stir it a little faster. Now, this reaction does not have any solvent. It's a neat reaction. And before we get it started, we need to add our amine. Now, our amine, you can see another very old bottle. This is morpholine. The procedure I'm following actually calls for piperidine, but I couldn't find piperidine in my lab, and I found some morpholine, which is structurally very similar. So I think I'm just going to go with this. Now, I have this in a pipette. You can see it's a little bit yellow, which is not uncommon for amines. I want to add 10 drops to this reaction. And so keep your eyes on the reaction. It may change color just a little bit. That's 1 drop of morpholine. There it goes. We're starting to get some yellow. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's always nice to see color changes. That's a sign that something is happening, and that's what we want. And this reaction now is just going to sit and stir. And I'm actually going to heat this up a little bit. I'm going to warm this up to about 70 degrees on the stir plate. I don't have my watch glass handy, but I will put a watch glass on top of this. And I'm just going to give that a little bit of thermal encouragement, 70 degrees. That's 70 degrees on the hot plate. It's probably not getting to 70 degrees in the beaker. I'll just let this warm gently, and we'll let this heat overnight, and we'll come back, and hopefully we'll have a nice change waiting for us. Well, this reaction has been standing or stirring for about 20 hours. And as you can see, it has completely solidified. So I think we're done with the heat. Let's turn that off. We can turn off the stir plate because that's no longer doing anything. And now let's look at this mixture. So this is completely solidified top to bottom, and it is just a touch warm on the bottom. So what has happened, and I checked this after about an hour, and it was starting to form some solid, but it was still definitely liquid in here. But now there's no sign of liquid. So what's happened is, as this stuff is precipitated, probably the more pure material precipitated first, and then as time went on, the very top was the last stuff to solidify. And this is, you can see that it's discolored. That's really where most of the impurities are. I'm not saying that this is completely pure in here, but this certainly looks less pure, at least based on color. So what needs to happen is I will try to break this up as best as I can and as finely as I can. And once I'm satisfied with that, you can see I'm kind of pushing this to the side and digging a hole there. Once I'm satisfied that this is fairly well broken up, we'll go ahead and transfer this to water. Now, I will note I'm a pretty big fan of using scintillation vials as reaction flasks, and I could have done that here, but a scintillation vial has a slightly narrower neck, and it would be a real pain to get in here and dig this stuff out with a narrower neck. So I'm glad that I used a beaker for this. That wasn't my intent, but as I work with this, I think, yeah, I'm glad I'm not confined to a scintillation vial and I have these straight walls of a beaker to work in. So I'm going to try to grind this up and break it up, and then we'll go on to the next step and try to isolate this product. Alright, now only a few minutes have transpired since I stopped the previous clip. And you can see I've broken up a fair amount of this. This is fairly loose in here. But as I break it up, this beaker is getting more and more full. So I need to put this excess solid that I've broken up somewhere. And I'm going to put it in a 250 milliliter Erlenmeyer flask, and I have a powder funnel in the top. And just to generate some volume, I'm going to dump this out. And now you can see I've sort of worked my way around here a little bit. I'm going to keep on breaking up this solid with this spatula. And once I'm done with this and I've transferred all the contents of this beaker that I can into here, then we'll go ahead and move on to the next step. Okay, now all this solid has now been transferred into this Erlenmeyer flask. There is just a little bit of solid in the funnel. We'll take care of that as we can. And just a little bit of solid left in the beaker. Really, this is a very small amount. I'm not worried about this too much, but we'll try to rinse this out a bit. Now, what I'm going to do is I'm going to mix this with about a 1% HCl solution. And when I say 1%, I mean this is about this is a 100 milliliter graduated cylinder. And I put in about 100 milliliters of water and added about 1 milliliter of concentrated HCl. So this is not 1% HCl, it's 1% times 0.37. But it's 1% volume to volume water to concentrated HCl. And I'm going to use this, mix this in the Erlenmeyer flask, do a little rinsing on the way, and then we're just going to let this stir. And we're going to let it stir pretty hard. And there are some chunks in here, and I'd like to break those up as much as possible. It won't be perfect, but let's just get it broken up as much as possible, because then the suspended solid we're going to go ahead and filter. So that was a long lead in. I've got a little bit of a pipette problem here. Let me fix that. That pipette bulb is coming off of the pipette. There we go, that's better. But this is just a really dilute acid solution. This is what the procedure calls for. It actually doesn't specify, it just says a dilute acid solution. You can say this material is not very soluble. It is not going to dissolve, which is fine, because there's very minimal loss in that beaker. Let's go ahead and take this 100 mils. Oh, let's put it through here, just in case we get a couple crumbs to rinse through. That's good. Now our product is just floating in a really dilute acid solution. Now to this, I'm going to add this big stir bar. This is kind of an overkill stir bar, but I really want this to stir and mix and hopefully break up any chunks in here. So let's add this down. That's fine. And now we want this to stir. And let's get this going pretty good. I may turn it up a bit. Now I'm going to let this stir. I'm going to let it stir for a while. Here's the watch class I had on the reaction. Let's put that back on there. I'm going to let this stir for quite a while, probably a few hours, and just see if we can more completely pulverize this solid to increase the surface area, let any impurities leach out of that solid, and then we'll go ahead and do a vacuum filtration. Well, this has been stirring for, I'd say, 2 or 3 hours. Turn off the stir plate, and you can see that's fairly nicely suspended. It's pretty fine. Now I promise you there are some bigger pieces hiding within that mess. But anyway, it is a lot finer than it was. And that was really the goal. It's never going to be perfect. We just need it to be good enough. So let's go ahead and filter this. I already have a 250 milliliter sidearm flask over here. We have a Buchner funnel and a filter paper in there. And let's spray a little water. So this, I'm using water to seat the filter paper. This is not water. It's that 1% acid solution, but that's essentially water. So I'll use water to seat the filter paper. Turn on. I'm not sure if you can hear that suction, but we're getting good suction there. That's nice. And I will just swirl this to get this nicely suspended. I'm going to pour this in. I'm going to try not to do the stir bar, but I'll see if I can be patient enough. Okay, that looks great. Oh, there are some pieces. See, you can't avoid the pieces, but that's okay. Now let's give this a little more water. I'm not gonna be patient enough to avoid the stir bar. We're just gonna dump everything in. The more firmly and quickly you pour it, the more you transfer the solid, but that means you're gonna dump the stir bar. You can always use a stir bar remover, but I don't have one in reach, and you know, that's how it goes. Okay, that's that's not perfect, but that's good enough for what we need. Let's just spray this down a little bit more, and I will show you what this looks like in the funnel. There it is. I mean, you can see there are some pieces in there. It's not all fine powder, but it's that's not terrible. That's not bad. I'm fairly content with that. So I'm just going to let this air dry now. I'll probably spread this out, put it on a watch glass, and get it nice and dry, and then get it weighed out, and I'll come back and show you what we got. Okay, well, this is back in the hood. Here is the product. It's been spread out on a watch glass. It's dry. You can see there are some bigger pieces in there, but I'm less worried about the bigger pieces from a purity standpoint, and it's more about the bigger pieces can trap moisture, so it takes a little bit longer to dry. This is dry now. This is 8.997 grams, so just a hair under 9 grams. This is going to be a good yield, which is not surprising based on the literature procedure that I've been following. But now we need to see that this looks like a good yield. We'll need to calculate a yield, but of course first we'll need to confirm that this material has good purity. So next will be a TLC, melting point, and an NMR spectrum. Let's start with the TLC. Here to the left is the TLC plate of the product. The mobile phase for this TLC is 50 ethyl acetate hexane. The spot traveled 1.8 centimeters. The solvent front traveled 4.5 centimeters. That corresponds to an RF value of 0.40. This TLC ostensibly looks like one spot, but the lighting is making the image overexposed. There is a bit of a streak toward the bottom of the plate. The TLC looks fine, but it's not the best start. Of course, this product is technically a crude product. This material has not been recrystallized, distilled, or chromatographed. The product just formed as a solid and was filtered. This is a crude product. How about the melting point? Well, the product melted over a range of 115.5 to 118.6 degrees Celsius. The literature value is 119 to 122 degrees Celsius. I pulled this melting range from this compound's Sigma Aldrich page. The web page is at the bottom of the slide. So my observed melting range was a bit low. That's often the case for me. I can never seem to match a literature melting point. Normally, however, my products have fairly narrow melting ranges. A melting range of 3 degrees is getting rather broad, so this is additional evidence that the product contains some impurities. Let's see what the NMR looks like. Here is the full NMR spectrum, the proton spectrum. This spectrum was performed in D6, DMSO at 400 megahertz. We have some aromatic signals downfield. The upfield signals are dominated by this singlet, which is the methyl group. On first glance, the product looks reasonably clean. The baseline is fairly clear of extra signals. Let's look closer at the upfield region. We have 3 upfield signals. 2 are from the DMSO solvent. Those would be the peaks at 2.5 ppm for DMSO itself, and the peak at close to 3.4 ppm for a bit of water in the DMSO. The large 3 protons hydrogen singlet at 2.6 ppm is the methyl group. Great, let's look downfield. The downfield region is far more interesting. We have 5 hydrogens total. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So everything is here. The downfield signal at 8.6 ppm is almost certainly the isolated proton HA. I won't go through all my thinking, but I would guess that HB is the doublet at 7.9. HD is this triplet at 7.7 ppm. The remaining 2 hydrogens are overlapping. You can maybe discern the doublet to the left. That would be HE. The remaining triplet is HC. This looks fine, but how about the streaking in the TLC and the broad melting range? Do we see evidence of impurities in this spectrum? I would say no, but there are some weak, broad lumps in the aromatic region. Those aren't major impurities, but they might be the origin of the yellow color in the product and some of the TLC streaking and depressed melting point. I think the product looks really nice for a crude product, but this material is certainly not pristine. Let's finish with a yield calculation. So the aldehyde has a molecular weight of 122.12 grams per mole. We used 6.11 grams of this material. That is 50.0 millimoles. For the ketoester, the molecular weight is 130.14 grams per mole. We used 6.52 grams for 50.1 millimoles. The morpholine is catalytic, so I'm not going to bother calculating stoichiometry for the base. For these 2 reagents, the aldehyde is the limiting reagent, and our theoretical yield is 50.0 millimoles. The product, 3-acetyl Coumarin, has a molecular weight of 188.18 grams per mole. We obtained 8.997 grams. That corresponds to 47.8 millimoles. This is the actual yield. If we take actual over theoretical times 100, we get 96%. We obtained a 96% yield. That is super high. Note that the literature yield from the procedure I referenced was 95%, and that 95% was also a crude yield based on filtration of the product following acidification. So this is a high-yielding, highly reproducible reaction. Of course, anytime you see a yield of 95 or 96%, you should wonder if there are some impurities inflating the yield. The TLC and melting range indicate some impurities, but the NMR, while not perfect, is reasonably nice. This is a fairly clean product for not being purified. Overall, I'd say this is a really nice procedure for making 3-acetyl-coumarin and a nice demonstration of the Knoevenagel condensation. I hope you enjoyed this example of the Knoevenagel condensation with salicylaldehyde and ethyl acetoacetate. This transformation and other aldol-type condensations are often simple, high-yielding reactions. Please subscribe, like, or leave a comment. Take care.